Welcome to G Fun Facts Online. Today we are diving deep into the silence of space to listen to the mind of a machine. Picture this. It is February 2026. The red dust of Jezero crater is settling on the titanium rims of the Perseverance rover. 140 million miles away, at NASA's Jet Propulsion Laboratory, a team of engineers is sipping coffee and waiting. There is no joystick in the room. There is no real-time video feed. There is certainly no brake pedal. They are waiting for a signal that confirms that for the last 2 days, their six-wheeled Explorer has been driving itself. It hasn't just been following a line on a map. It has been thinking its way through a labyrinth of Martian boulders. For decades, planetary exploration was a stop-and-go game. It was a painstaking waltz where human operators moved a rover a few meters, took a picture, waited 20 minutes for the signal to reach Earth, planned the next move, and sent it back. That paradigm is dead. We have entered the era of the autonomous agent. As humanity pushes toward a permanent presence on the moon and sets its sights on the icy moons of the outer solar system, the vehicles we send ahead are no longer just remote-controlled cars. They are geologists, cartographers, and decision-makers. They are powered by onboard neural networks, cooperative swarm algorithms, and increasingly, the same generative AI architectures that power chatbots on Earth. Today we are going to explore how artificial intelligence pilots vehicles on other worlds, from the tracks of Perseverance to the swarm intelligence of the upcoming K-Dray mission and the flying eyes of Dragonfly on Titan. To truly understand the sophisticated autonomy of 2026, we have to look back at what we might call the Stone Age of planetary roving. When the Sojourner rover landed on Mars in 1997, it was essentially a reactive insect. It had a simple hazard avoidance system based strictly on laser striping. It would project a laser beam, and if that beam did not hit the ground where expected, the rover essentially panicked and stopped. It was safe, but it was agonizingly slow. Then came the Spirit and Opportunity rovers in 2004. They introduced a concept called visual odometry. This was the first step toward true self-awareness of motion. By comparing successive images of the terrain, these rovers could calculate exactly how much they had slipped in the loose sand. This was a critical capability. Imagine sending a command to drive forward 1 meter, but your wheels spin in the dust and you only move 50 centimeters. Without visual odometry, the rover would think it had reached its destination. With it, the rover knew it had fallen short. Then came Curiosity in 2012, which upped the ante with AutoNav, or autonomous navigation. For the first time, a rover could build a local map of keep-out zones. Human drivers would define a safe corridor, and Curiosity would pick the specific path inside that corridor. However, this was computationally expensive. Curiosity had to stop frequently to take images, process them with its limited onboard CPU, think about the result, and then drive again. It was a stop-think-drive rhythm that limited autonomous travel to a few dozen meters an hour. The game changed when Perseverance landed in 2021. It brought a dedicated computing element specifically for vision processing. This allowed for enhanced AutoNav. Perseverance does not stop to think, it thinks while it moves. Its cameras snap wide-angle photos, and an onboard field programmable gate array processes the stereo disparity maps instantly. The path planning algorithm updates the trajectory in real time, allowing for a fluid, continuous drive. By 2026, this system has evolved even further. The most significant recent leap has been the integration of generative AI into the planning loop. In late 2025, JPL conducted a historic experiment involving Claude, a large language and vision model. Traditionally, path planning was a geometric problem. The computer asks, is this rock too high, or is this slope too steep? But geometric planners lack semantic understanding. They see a geometry that looks like a rock, but they do not understand context. They might not realize that a specific texture of sand ripple is a dangerous trap, while a flat bedrock slab is safe, even if the geometry looks similar. In the 2025 tests, engineers fed the AI high-resolution orbital imagery from the Mars Reconnaissance Orbiter and surface-level NavCam data. The AI was not just asked to find a path, it was asked to reason about the terrain. The prompt was simple. Plot a path to the crater rim that avoids high-slip sand zones. The model analyzed the visual textures, identified sand traps that geometric filters might miss, and generated a series of waypoints encoded in Rover markup language. The result was stunning. The AI-generated path was 95% identical to what a senior human rover driver would have plotted, but it was generated in seconds rather than hours. This semantic navigation capability allows Perseverance to handle complex terrains that would previously have triggered a fault and stop condition in classic AutoNav. While NASA focused on the speed of autonomy, the European Space Agency, or ESA, has been refining the precision of autonomy for its Rosalind Franklin rover, scheduled for a 2028 launch. The challenge for Rosalind Franklin is fundamentally different. It carries a heavy, 2-meter-long drill. Navigating is not just about avoiding a crash. It is about positioning the vehicle with millimeter-level accuracy over a drill target without sliding. The Rosalind Franklin navigation architecture draws from the Rapid and FAST-NAV development projects. Unlike the early NASA rovers that relied heavily on wheel odometry or counting wheel turns, the European rover places primary trust in its eyes. The system uses a multi-resolution mapping approach. First, global path planning uses orbital data to map out a course route of several kilometers. Second, local path planning uses the rover's navcam and localization cameras to build a dense 3D disparate map of the immediate 20 meters. Third, and most importantly, it uses visual SLAM, which stands for simultaneous localization and mapping. As it moves, the rover tracks feature points, such as the distinct sharp edges of rocks or crater rims. By triangulating these points frame by frame, the rover knows its position relative to the start point without needing a GPS, which, of course, does not exist on Mars. The crucial innovation here is the drill positioning system. Once the rover arrives at a science region of interest, the autonomy shifts from driving to manipulation. The rover must use visual servoing to align its drill box with the surface, compensating for the suspension settling on soft soil. This is a level of autonomous physical interaction that goes beyond mere driving. Now, let us leave Mars and travel to the Moon. The Moon is witnessing an explosion of robotic activity in 2026, driven by the Artemis program and the Commercial Lunar Payload Services Initiative. The autonomy challenges here are unique, because the lighting conditions at the lunar South Pole are brutal. There are long, pitch-black shadows that confuse standard cameras. This has led to the LTV, or Lunar Terrain Vehicle, wars. NASA has selected 3 commercial providers to develop these next-generation moon buggies. These are unpressurized rovers that astronauts can drive, but which must also operate autonomously when the crew is gone. The first contender is Intuitive Machines, with their Moonracer. They partnered with CSIRO, Australia's National Science Agency, and AVL. Their technology uses a LiDAR-first approach. While cameras struggle in the high-contrast lighting of the lunar pole, LiDAR brings its own light. The Moonracer scans the terrain with laser pulses, building a high-fidelity point cloud. They utilize a technology called Wildcat SLAM, originally developed for autonomous mining in GPS-denied caves on Earth. This allows the rover to localize itself by matching current laser scans against previous ones, effectively seeing in the dark. The second contender is Venturi Astrolab with the Flex rover. Flex stands for Flexible Logistics and Exploration. Think of this as a flatbed truck for the Moon. Its autonomy is focused on logistics. The rover is designed to use intermodal autonomy. It can autonomously crouch down, drive under a cargo module that looks like a shipping container, lift it up, and transport it. This requires docking autonomy, which is the ability to align mechanical interfaces with sub-centimeter precision using visual fiducials, similar to QR codes. The third contender is Lunar Outpost with the Eagle rover. They have partnered with General Motors to leverage the massive investment in self-driving cars on Earth. The Eagle rover uses a condensed version of terrestrial autonomous driving stacks, adapted for the lunar regolith. Their Mobile Autonomous Prospecting Platform, or MAP, has already demonstrated swarm capabilities, where multiple small rovers move in a search pattern to map magnetic anomalies. Speaking of swarms, perhaps the most futuristic mission of 2026 is NASA's CADRE mission. CADRE stands for Cooperative Autonomous Distributed Robotic Exploration. This mission landed 3 shoebox-sized rovers on the Moon to test multi-agent autonomy. In traditional missions, a human operator is the central brain. In CADRE, the brain is distributed. The heart of the system is MoonDB, a distributed database that lives across all 3 rovers. When Rover A sees an obstacle, it updates its local MoonDB. This update is propagated to Rover B and Rover C via a mesh radio network. This allows for leader election. The swarm uses a consensus algorithm, similar to those used in cloud computing, to elect a leader. If the leader rover falls into a crater or its radio dies, the remaining 2 detect the silence, hold an electronic vote, and elect a new leader to coordinate the mapping task. They also use cooperative stereo. One small rover cannot see depth accurately at long range. But if Rover A and Rover B stand 10 meters apart and look at the same distant mountain, they can function as a giant, synthetic pair of eyes, calculating distance with massive baseline capability. This is distributed sensing, and it requires the rovers to autonomously coordinate their positions relative to each other. Finally, we must look beyond the inner solar system to Titan, the moon of Saturn. If driving on Mars is hard, flying on Titan is a nightmare of autonomy. Dragonfly, NASA's rotorcraft lander scheduled to arrive at Titan in 2034, is being finalized now. Titan has a thick atmosphere which is good for flying, but it is dim and featureless in many areas. Dragonfly uses visual inertial odometry. It lacks the luxury of stopping to think. If its software hangs, it falls out of the sky. It uses a tight coupling of inertial measurement units and cameras. The IMU gives a fast, high-frequency guess of position, essentially telling the computer, "I felt an acceleration forward." The camera then corrects that drift 30 times a second by tracking the flow of pixels, confirming that the ground is indeed moving backward. Dragonfly employs a unique autonomous behavior called the leapfrog strategy. It will never fly blind into the unknown. First, it sits at Site A, it takes off and flies to Site B, which it has already seen and validated. While hovering over Site B, it uses its sensors to scan a future Site C. Then, it lands back at Site B. By doing this, the autonomous navigation system always has a pre-validated map for its landing zone, significantly reducing risk. But autonomy is not just about moving, it is about doing science. Bandwidth from Mars is limited. A rover might collect 100 gigabytes of data but can only send back 500 megabytes a day. Who decides what to send? This is where AEGIS comes in. AEGIS stands for Autonomous Exploration for Gathering Increased Science. Running on Perseverance and Curiosity, AEGIS analyzes images after a drive. It uses computer vision to find rocks in the scene. It filters them based on scientist-defined criteria, such as finding bright white veins or large, dark basalts. It then automatically aims the SuperCam laser, zaps the rock to get a spectral reading, and prioritizes that data for downlink. In 2026, this is evolving into onboard science captioning. Instead of just sending back raw numbers, onboard AI models analyze the spectra and image to generate a text summary. It might send a message saying, "Target A has basaltic composition, with high silica content and a possible hydration signature." This allows scientists to read a text message from the rover before deciding which heavy image files to download. We are witnessing a fundamental shift in the nature of exploration. The rovers of the past were tools. They were extensions of human will, tethered by the long, invisible string of radio commands. The rovers of 2026 are partners. When Perseverance uses a vision language model to navigate a boulder field, or when the Cadre swarm votes on a new leader after a failure, they're displaying a primitive form of agency. They are not just surviving the alien environment, they are understanding it. As we look toward the 2030s to the human-robot teams of the Artemis moon base and the solitary flight of Dragonfly through the orange mists of Titan, one thing is clear. The first intelligent life we find on other worlds will be the life we built and sent there. Thank you for listening to this episode of G Fun Facts Online.